An interstellar object known as 3I Atlas has reportedly lost nearly 99% of its mass in less than 3 months. According to classical physics, such a loss should produce debris, explosions, or visible disruption, but none of that was observed. Instead, the object remained intact, silent, and mathematically inconsistent. How can an object lose tens of trillions of kilograms without breaking apart? Was the mass ever truly there, or were our assumptions incorrect from the start? And what does this anomaly reveal about how we measure objects beyond our solar system? For more science-based breakdowns of space anomalies, subscribe to the channel, like the video, and hit the bell icon. 3I Atlas is classified as an interstellar visitor, an object that did not originate in our solar system. Early measurements suggested it was enormous, with an estimated mass of 33 trillion kilograms and a diameter of several kilometers. These conclusions were not based on speculation, but on motion, or more precisely, the lack of motion. Between late spring and early autumn, over 230 observatories worldwide tracked this object continuously. Its trajectory followed gravity almost perfectly. There was no detectable acceleration from solar radiation, no visible gas jets, and no deviation from predicted paths. In physics, this absence of movement is meaningful. When sunlight strikes an object in space, even weak outgassing should cause measurable changes in velocity. If nothing moves, the object must have high inertia, which directly implies high mass. Based on this principle, researchers calculated that 3I Atlas had to be extremely heavy to remain so stable. The margin of observational error was exceptionally small, on the order of 0.028 arcseconds, a level of precision that rules out casual miscalculation. At that stage, the massive object model appeared consistent with every dataset. This interpretation was widely accepted, including by teams working with data linked to NASA. The object behaved exactly like a large, inactive body drifting through interstellar space. No forces appeared to be acting on it other than gravity. However, this entire framework relied on one critical assumption, that the object's silence meant solidity. As 3I Atlas continued its approach towards the Sun, researchers expected increased activity. What they did not expect was that later measurements, especially those involving propulsion effects, would fundamentally contradict the original mass estimate. This contradiction became unavoidable once more sensitive instruments were applied, including observations associated with the James Webb Telescope. For the first time, a small but measurable acceleration was detected. That single measurement forced scientists to rerun the physics, and when they did, the numbers collapsed. The object could no longer be massive. To produce the observed acceleration from gas release, 3I Atlas had to be dramatically lighter and smaller than previously believed. At this point, the original model stopped working. Once the revised calculations were applied, the estimated mass of 3I Atlas dropped from 33 trillion kilograms to roughly 260 billion kilograms. That is not a minor correction. It represents a reduction of more than 99%. The cause of this revision comes directly from measured acceleration. The object was observed gaining roughly 13 kilometers per day in velocity due to outgassing. Spectroscopic data indicated gas leaving the surface at approximately 1,600 kilometers per hour, with a mass loss rate near 150 kilograms per second. When these values are combined using standard momentum transfer equations, the result is unavoidable. An object with the previously assumed mass would not accelerate measurably under such weak thrust. Therefore, the object must be far lighter. Physics does not allow both models to be true at the same time. Either the object was once a massive body that lost nearly all of its mass without leaving debris, or it was never massive to begin with. This is where the anomaly becomes significant. If 3I Atlas had always been this lightweight, solar radiation pressure should have affected it months earlier. Yet, during the initial observation period, no such movement was detected, despite extremely sensitive measurements. That absence of acceleration conflicts directly with the low mass model. Some researchers propose that the outgassing was highly directional and previously undetectable. Others suggest a fluffy comet structure, an object with extremely low density that behaves differently from solid ice or rock. However, these explanations struggle to reconcile both phases of observation at once. An alternative interpretation has been discussed by scientists such as Avi Loeb. This hypothesis suggests that the object may not be a solid body at all, but instead a thin, hollow structure. In such a case, its apparent mass at large distances could be misleading, while its later acceleration would be easier to explain. A hollow or shell-like object would interact differently with radiation and gas release. Its cross-section could remain large, while its actual mass stays low. This removes the paradox of the missing trillions of kilograms, because that mass may never have existed. It is important to note that this interpretation does not rely on speculation alone. It emerges from attempting to satisfy all observed constraints simultaneously: early-stage inertia, late-stage acceleration, and the absence of debris. At present, no single model fully explains every measurement. Natural explanations remain under active investigation, and no official conclusion has been reached. However, 3i Atlas has already demonstrated that current classification systems for interstellar objects may be incomplete. Whether it was an unusual comet, an extreme low-density structure, or something not yet categorized, the object exposed a limitation in how mass, motion, and silence are interpreted in deep space. As 3i Atlas exits the solar system, it leaves behind two incompatible datasets and the gap of 32 trillion kilograms in our understanding, not necessarily in matter, but in assumptions. The lesson is not that physics failed. The lesson is that physics worked perfectly and revealed that our starting assumptions may have been wrong. 3i Atlas is no longer observable in detail. What remains is a rare case study showing that interstellar space may contain objects that do not behave like traditional comets or asteroids. And until another visitor arrives, this anomaly will remain unresolved.